I think we're about to start. And today we have Sara Hooker. Thank you for coming. And she's a VP at Cohere. She leads a research team, Cohere for AI, right? She has worked before on Google Research Brain. And before that, she founded or co-founded Data Analytics.
Yeah, Data Analytics.
Non-government organization.
Yeah.
She did very inspiring work. So it's a pleasure to have her here today and give us a talk. And so hope you like it.
Oh,
The
that's
floor is yours.
lovely. Thank you. And I guess I don't need that. That was lovely. That was very impressive from memory, whole introduction. That was really nice. Thank you. It is so lovely to be here. Thank you so much, everyone. It's like already been a really nice experience having conversations with many of you. I thought since we have an hour today, instead of trying to convey a lot of information, I'll talk about a topic that has been on my mind recently. And I'm going to talk about really, maybe I'll share briefly. So Cohere for AI is a fundamental research lab. We do research. We also have some very large open science initiatives. Maybe the one you've heard of is probably Aya, where we did a massive multilingual collaboration all around the world, and we released Aya models. Maybe I'll skip this. One thing I will mention is we also offer research compute grants. So many of you are doing research. If you're interested in this, feel free to check out the website, and we try and support researchers in doing fundamental research. So this might be of interest to some of you. Okay, today I thought it would be interesting to talk about a recent paper I released. So I currently work on designing large-scale language models that are efficient, multilingual, reliable, trustworthy. So those are all topics I'm happy to talk about over the next few days. And please find me. It will be nice to hear about your interests and how they relate. But today I'll be giving a talk about a paper I recently released. This paper is unusual for a few reasons. I was talking to Fernando before the break, and I was saying I rarely have time to write anymore. So this paper is unusual because I was able to release it. I worked on it since February. And at this moment in time, for me to be able to release a paper, especially with all the projects in the lab and supporting others, it has to be something I'm really angry about. So this is a grumpy paper. And so maybe that's fun for us to think about today. This is also unusual because it's a paper in some ways about a very boring policy topic. And I'm a technical computer scientist, as many of you are. And so it's unusual to be weighing in on this, but I think that's a reflection of the time we're in, where our models are used everywhere. And this paper was about this increasing trend to create risk with more compute. So the idea is that there's certain levels of compute where a model takes on a new risk profile. And the idea is that also this is where more scrutiny should be applied. And so I kind of ask in this paper, firstly, is that true? What do we know about the relationship between compute and performance? And secondly, are we good at predicting what risks emerge at certain scale? What's our track record? How good are we at predicting the future? Especially because all these compute thresholds don't apply to current models, they apply to future levels of compute. But today, I won't talk about the policy aspects. I'll actually just talk about these technical aspects of the paper. And in particular, what do we know about the relationship between compute and performance? But if you're interested in that second question of are we good at predicting at scale, you feel free to go read the paper. The short answer is no. We typically overestimate our ability to predict and to extrapolate beyond the models that we have. But I'll leave that for a separate talk, since it'll be fun to dive in more to this one. And you see why this is interesting, why I thought this would be interesting for our group here, is that to really address this question of are compute thresholds useful, we have to tackle a question that's been at the center of our field for the last 2 decades, which is bigger always better? Is compute the most surefire way to gain performance in models? And that's what we'll start with. We'll start with the role of capacity. And to think through, we'll talk about model scale and data and recent breakthroughs. So in some ways, the evidence is quite convincing. And I'm going to have to make a difficult case today because by many trends, we are obsessed with throwing more compute at problems. So we have larger and larger models that have gripped the field of machine learning. This is an image from 2019. So actually, it only gets worse from here. It actually just goes abruptly up. And this characterizes all of our domains, right? So vision, NLP, we have massive gains in both compute size in terms of training time, as well as in terms of volume of data. And here, this is talking about the number of tokens used in training. And so really, we're seeing an escalation of capacity in multiple directions. Often we train for longer at the same level of capacity. Often we go bigger in terms of the number of weights of a network. But we also just add a lot more data. And so these different axes of capacity have kind of are essentially very strong points in the favor of bigger is better. So I have a hard task in front of me today to try and convince you that maybe we should be grumpy about this formula. This is being formalized by Rich Sutton as the bitter lesson. Who has read this blog post? Okay, bravo, nice, excellent. I think it's a really nice I would also encourage you, for those who have read it, to also read Max Welling's blog post, where he has a counter argument about the benefit of priors. But this idea about the bitter lesson, what does it say for someone who read it? I thought I saw a hand up over there. Who wants to quickly try and summarize? Oh, I see how everyone who was so quick to put up their hand is a bit shy now. Well, throw it out. Who would like to guess? Go ahead. Yes, just throw it out. I'll try and repeat what I hear. So we won't be able to wait because I'm going to do a lot of back and forth. Go for it.
Most of the algorithmic work we do at the end turns out to be search in some high dimensional space.
Yes. Okay. So well, I don't know about the high dimensional searching some high dimensional space, but basically, kind of in a punch to the ego of computer scientists, what Rich Sutton is saying is that really our attempts to codify, in particular, I think a lot of his argument is premised on symbolic approaches, but really what he's saying is a bit broader, which is that any attempt to create strong priors of how we think a model should learn has been a failure compared to just throwing more compute at a scalable problem. So this is very important. So very nice. Yeah, okay. And we can come back, we can have a redemption tour on this side of the room for people who raised questions there. So is Sutton right? Who wants to weigh in? Who wants to weigh in? Courage. We got to have some fire. Yes, throw it out. I'll try and repeat so we don't have to, yeah. Yes, so what you're raising is an excellent counter, I guess, in some ways a counterpoint, which is that when we have an architecture, and this is one of the things we'll talk about, in some ways it is a prior. What do we mean by that? Why is architecture a prior? Yes. Yes, you can imagine, I mean, the most explicit version of this is a polynomial where you can up the degrees of a polynomial, it becomes more expressive. This is probably what you all did in your intro to machine learning course. But even choices about the building blocks of modern architectures in some way express a preference for degree of expressiveness in the search space. So this is very nice. What else? So I guess that was a counterpoint, maybe grumpy about Sutton. Yeah, but what's another view? What do we think? Go ahead, excellent.
Just don't have enough data.
Yes, so I guess this is a very practical constraint. What's being said is some problems we just don't have sufficient data. So the Rich Sutton solution does not stand. This, by the way, is Max's excellent point in the counter blog post, which I recommend everyone read, is that priors are quite useful when we don't have that much data. And there's a tipping point where you can remove priors, but many problems in the world do not have much data. Very nice point. One more point here? You want to come back for round two? Okay, let's do the gentleman there first, who's joining. Yeah, and then we can go back to the original person. Yeah.
Yeah, but as far as I understand, it's not so easy to get a model from data.
So pardon, go ahead, repeat that one.
It's not so easy to build a model for data. So actual models do not build models.
Okay, what
They
I
build systems, but not models of the reality.
see, I see. So you're talking about the difference between a model and a system.
Yeah, humans producing a model about the problem with priors and so on, and then you deliver an implementation of the model that works or not according to the specifications.
Yeah.
How an artificial system is going to do that nowadays? And explain us what it has done. How?
Yeah, okay, that was a question at the end. Okay, so we'll come to that. I do think what you're saying is this idea that we often obsess with the notion of the algorithm, but there's a system, there's a wider system which an algorithm sits, and this is typically the most frequent in terms of deployed systems in the wild. And there, the interaction of how performant it is not just a facet of the model, it's how the model interacts. Like, for example, a good example of this is recommendations. I saw a poster that was still up about Spotify recommendations. Anyone who's worked with recommendations or deployment system knows that when you intervene on the data, you cause changes to the data distribution. And so that's a good example of that, of like, yes, their scale is not sufficient because your data distribution may be changing and the model may fall out of freshness, which is a good example. So I will say, I'm first going to take the cap of Sutton is right. Here's more evidence. Oh, okay, we'll get to you. Don't worry, there'll be another moment to intervene. I'm going to come back to you. So different regimes of scale induce what people have frequently called emergent abilities. We can have that debate separately about whether they really are emergent, but they are persuasive. One of the reasons people like this formula is it does appear to be new properties which emerge as you scale. So frequently it's things like coding ability or things like multilingual. And we know, for example, that certain properties like instruction fine-tuning, you need a certain scale to realize zero-shot performance. And so there are, there's a reasonable quantitative support for why we like this formula. And so we tend to still like to throw compute at the problem. I also think this is largely because it's the most de-risked approach. So if you have to justify something, it's easier to say, oh, I think we should throw compute at the problem over the next few months than to take a more hypothesis-driven approach. Alas, that is the realm that we are now in as a computer scientist. And unfortunately, it also, whoever's been in industry, it's really unfortunate that throwing more compute at the problem fits really nicely into this quarterly planning cycle. So you're like, okay, cool, let's lock it in. This is our compute, let's go. So it's hard to justify deviating from this formula of just throwing more compute. But there's many data points which exist to show that training compute alone is not sufficient, or at least doesn't tell the full story. So one is models at the same capacity have become far more performant over time. So this is just the Hugging Face open leaderboards. This is just plotting models under 13B. So 13 billion parameters or lower. I know we had that fantastic presentation about BERT earlier, and that was 400 million parameters. But now 13 billion or lower, I would consider a small scale model. These are ones that fit typically under a single device. And we see that even these have become more performant over time. The second is that smaller models frequently outperform larger models. And so this is the same plot of the best daily 13 billion or smaller model submission on the OpenLLM leaderboard against any larger than 13B model, which performed worse. And actually the size of here, the dots, speak to the size of the model. So you can see there's massive models that perform worse than 13B models. And anecdotally, you probably know of some of these models, right? So we released Aya 23B, that's an 23 language, that's an 8 billion parameter model. And it outperforms, for example, Bloom, which is a 176 billion parameter model. So these are drastic differences. And these were released different years, right? So something we're going to think about together is what's changed, what allows these far smaller models to outperform much larger models. But this is a clear counterpoint that compute or scale is not everything, and that there's meaningful changes in how we're using capacity that don't require simple compute. And I would say a key limitation of following the beta lesson is that the relationship between compute and performance properties is poorly understood. We don't have a good understanding of what is the rate of return for additional compute. And this is perhaps the most imprecise aspect, is that we throw compute at the problem, but we don't have a good or precise articulation of what we're hoping to gain. We just kind of press play and hope at the end that it's baked enough or it's enough compute that the model is great. So in fact, we observe a highly uncertain relationship between compute and performance. Okay. So what are some factors that impact performance of a model that are not just compute? Okay, yeah, let's go there and let's go here to the gentleman. Actually, let's start here. Inductive biases. So we heard a little bit about this, right? We heard about the architecture. This is very important. So architectures have a form of inductive bias that kind of conditions the search space. Yes, and then over there. Data. Yeah, fantastic. We're going to talk about that. Yeah, in what sense does data, skew this relationship? Yes, precisely. Okay, this is fun. We're going to talk about quality. Okay, way up there. Yes. Yes, certainly. So you could argue that here, this plot of the Hugging Face Open Leaderboard, that maybe some of this trend is due to test set leakage, because when you train on the internet, it's hard to distinguish what you mean by a test set anymore. So that's a very nice counterpoint. I would argue that you would expect this to equally impact both large and small still do better than large. So it's probably not the only thing, but I do agree. Our notion of how we evaluate models is in crisis. So this is another aspect that we expect. So very nice point. I like that a lot. Yeah, what else?
There's also the optimization problem that you solve. That is the
Okay.
loss function that you decide to use and the algorithm that you use to solve that problem.
Yes, I do agree. The objective is very interesting. We're going to talk about some of the innovations in objective a little bit later. I do love that you secured a microphone. Wow, this is great. Yeah. What else? Okay, maybe we thought, go ahead.
It's speculative. I'm not aware of anybody who's thought about enumerating all orthogonal independent contributing factors to quote unquote.
I tried to do it in this essay, but I did not succeed. But I do think it's there are many things that impact performance. In many ways, that is the study of machine learning. The notion of performance is up for debate. I think that this is valid. I think that's partly what's being raised with the question about, well, what is the test? What are we getting better at? What is performance? But there's also fundamentally the question of what do we rely on as our key levers of improvement? And maybe that's the crux of this, is that there's a consensus in our field that one of the key levers is compute. And perhaps this is increasingly being stress tested, that this is the way that the key lever that we should be exploiting for progress. Okay, any one more comment here? Any other thoughts? Yep, go ahead. Yes, hardware algorithm compatibility is a huge one. So I actually don't talk about this here, but I do talk about it in another paper, the hardware lottery. I think it's very underestimated, the ability of progress and pace of progress that comes from making those cohesive, because our tools are often not. We recently did a work on software portability where we found that 46% of PyTorch functions are not portable to TPUs. So there's this whole stack notion of what are first-class citizens on different types of hardware. And we take it for granted. We just stick within the stack that we have. But it's actually very detrimental to easy fluidity and portability of ideas. So that's a very nice point. And we won't talk about it here, but that's very excellent. Yeah. Okay. Yes, go ahead. Nice. Yes. Yes. Yeah. One would hope. One would hope. No, but it's true. I mean, this is a very interesting understudied aspect of science, contagion effects. And so right now we're actually in this interesting stage where industry labs don't publish as much. And it's very interesting how it's created fractured states of progress where you bump into someone and they might tell you what they think was the underlying optimization technique between this. And so it is non-trivial. It's who you work with, and it's the way in which ideas are shared and how ideas are put together. I completely agree. This is very nice. Okay, nice. This is good start. This is very good. Okay, let's talk about a few topics that I think are relevant for this premise that Rich Sutton is at the notion of the bitter lesson is at, it is in some ways, it fails to capture the changing state of our relationship with compute. I don't dare say wrong because the empirical evidence is stacked against me, but I will say that it seems increasingly clear that the levers of significant progress are not compute alone. So excellent. We kicked off with an excellent statement from the lady over there, which was that data quality compensates for the need for compute. This is very true. So recent work finds that higher amounts of high quality data compensate for the need of model. And so this is actually a simple step as deduping, but also pruning techniques, increasing the available training corpus for data. So these are all techniques which are very much centered on how do we reduce the amount of available trained data, but skew the distribution so that it's more like the downstream distribution we want to serve. And I want to highlight here why this has been such a pivotal axis of exploration for large language models. Why has this been in particular so lucrative as a direction for language modeling? Go ahead. Wow, someone works on data quality, I can tell. Fair. So there is an issue of what quality looks like for other domains, and maybe plausibly it's easier for language domains. Yeah, but why is it being particularly so beneficial to focus on data quality for language modeling? Yeah, go ahead.
By selecting or rating or biasing it,
Yes.
you are skewing it, which you know what kind of bias you want to put in there.
Yes.
Doesn't necessarily mean that your biases are necessarily not included.
Yes, so that's actually a fair point. So I guess this is fun because I feel this is fun because I'm getting instead commentary on how this is a difficult problem, which is also true. This is very difficult. So one is that what is your metric of quality? The second is you are introducing a bias. The notion is do you skew it? In that answer, however, there's also the response for why this has been particularly beneficial for language. Yes, go ahead.
What kind of data? When you do RLHF, it's kind of natively interpretable.
Yep.
Give some, at least with respect to particular viruses.
Yeah, this is.
You can generate.
Yeah, this is very true. So you can, this is gets the notion of how do you measure quality, and you could have, for example, preferences where if you have enough human annotations, you can do it. Yeah, but why does it matter so much? Why is it? Yeah, go ahead. Yes, so this is why it compensates for compute. This is why we end up with shorter training. I would argue why it's particularly beneficial for language is that this is where we have the biggest discrepancy between our traditional notions of train and test. So, other measures or other domains like computer vision for a long time, your notions of train and test were a bit awkward, right? ImageNet was often treated as if it was a single class data set, but anyone who worked with it could see there was multiple objects in a frame. So it was a bit hard to make progress on it at a certain point, but at least the data set was similar to the test that you want to train on. When we move to expensive pre-training on large corpuses of data from the internet, often there's a sharp break in what you train on, but also what you hope to deliver downstream. And increasingly, what we hope to deliver downstream is very eloquent, fluent generations, which are connect, retrieve information correctly, precise. And is this the internet? You can all say no at once, like, no. And that's the real reason I think here this has been such a good lever for minimizing the compute needed, is that because we were using so much compute to learn data that we didn't actually want in terms of downstream properties. And so skewing here is particularly impactful. And whenever you don't have a way to sample IID for the actual distribution you want, pruning or skewing that sampling is going to benefit. But as a, okay, yes, go ahead, nice. Yeah.
Make that kind of perspective, the data and the objective that we're solving. If we have
Yes.
the metric.
Yes, yes. And I think this is, yeah. And I'll come back to this in a bit when I talk about how we can now optimize more in the data space explicitly. But this is fun. So I think this changes the notion of axes of capacity. So typically when you have more data, you can push out the frontier. So you can do more with less compute and less training time. And so what this means is that it shifts out our production possibilities frontier. And we did recent work which focuses on effective data pruning at scale. So we showed this at a pre-training level. This is work led by Max, and it shows that you can remove up to 70% of the pre-training data. So this is internet scale pruning while preserving performance in your downstream tasks. I think this is very important direction of work. The key technical constraints here are exactly as described. How do you estimate quality? This is very crucial. But also for scale, how do you do it in an efficient way? This is kind of the dominant concern when you're at pre-training sites. I also think that what another point that was gone out with discussion of preference data, this is valuable at multiple stages of the pipeline. So we also look at this in terms of how to prioritize data annotations for human annotation, which is typically very costly. So you want to prioritize very good examples that are more likely to require some human arbitration. But also we've done a lot of work on how do you kind of prioritize for preference training itself, and how do you isolate some examples which are much more likely to require some investment in preferences and synthetic data generation as well. So these are all ways that you can bend the curve. I would also say one of the key counterpoints for simply adding more compute is that the relationship between weights and performance tends to not be well understood. So we have diminishing returns to adding more parameters. We see this actually in all domains. We also see this in language modeling. We famously saw this a lot in computer vision. So if you look at Inception v3, Inception v4, these are canonical models. But you would often double the number of parameters and only see an increase of like 2 percentage points in accuracy. And we increasingly see this in language modeling. There are a lot of redundancies between weights. And so you have a high degree of correlated weights. So this is a really lovely paper that shows that you can predict all the weights in a network using a tiny holdout. What this is saying is really these are all very correlated. This is also the reason you can remove the majority of weights after training. So this is a paper we worked on called the state of sparsity, and we compare all these different pruning techniques at scale. What we find is even if you remove weights at random, complete random, you still preserve majority of performance, and you only see sharp declines at 99% pruning. That's kind of crazy, right? It's really saying after you train, your representation is so robust, you don't even need majority of weights that you started with. So what are all those weights doing, and why do you need them to begin with? And then a lot of my work over the last few years has been showing that what you really lose when you remove the majority of weights, and we'll talk a little bit about this in a bit, which is that you lose performance on the long tail. So the majority of weights are used to memorize these very rare artifacts. And so you're really losing performance on this tiny part of the distribution. And that means that we have very inefficient representations. So it means that even though people might like to use compute as a lever for the most gains, it's a very inefficient lever. And it's probably only going to take us so far because we're using it in the most expensive way possible. So compute also does not capture the algorithmic breakthroughs that have led to large gains of performance over the last 5 years. So what are algorithmic breakthroughs? What have we seen? What are some important algorithm? Not architecture, algorithmic. So we can call this algorithmic or optimization breakthroughs. What do we have? Oh, Adam. Okay, cheeky Adam. Yeah, you can squeak that in. Okay, so Adam, that's a good one of an optimizer. Yeah, but yeah, what about over the last 5 years? What are we seeing? Pardon? Both. Both. Yes, let's dream big. Yeah. Oh, go ahead. Yes. Laura's adapters, that's definitely helped with efficiency. It also has helped with adaptation. Okay, technically it's an architecture adaptation, so maybe up for debate whether it's just purely optimization technique, but I feel like you could probably make a debate about anything, like where does it sit? So yeah, okay, we'll take that. Yeah, what else? Go ahead. Yes, distillation. We brought up data quality. Distillation has been really pivotal for imparting a lot of performance and kind of imparting performance of much larger models. Very nice. Yeah, what else? Pre-training, yes, this is certainly a very recent development. So pre-training was largely not believed to be successful, and then it was shown to be successful, not in the last 5 years, but definitely in the last decade or so. The move towards pre-training has been really impactful. Okay, and pre-training only worked with a certain amount of scale, so it's kind of an interesting one in that sense. It's actually scaling the amount of data. So I'm not sure I could argue that it was that it supports the stance that scale is not important, because in fact, it only worked with scale, but it is a fun example. Yep, go ahead. At the back, we have 3 hands in a row. This is fantastic. Oh, 2 hands in a row. Yeah. Go for it. I will repeat
Oh,
back.
I have the mic, so I'll go.
Oh,
Reinforcement learning from human feedback.
yes, bravo. Nice. That's on the bingo card. Yep.
Quantization.
Quantization. Interesting. Technically, quantization often degrades top-level performance. It does improve efficiency, so it depends on what your objective of performance is. But it has certainly become more critical given the size of networks. Yeah. What else? Okay, yes, go ahead. Yes, it certainly counts. That's on the bingo card. And actually, that's one where it doesn't take much compute. So the structure matters. So actually, the lady said instruction fine-tuning, right? That's my understanding. You said fine-tuning? Okay, so yes. Okay. So yes, instruction fine-tuning has been shown to be quite efficient because of the formatting of the prompt and completion. Turns out you need not much data in that format to produce large gains. So I do think that's a great example of a very compute light measure that dramatically improves performance. So very nice. Yeah. Anything else here? Yeah. Yes. Bravo. That's on the bingo card. So yep. I think there's been very nice, and that matters in a few. That's part of the inference. I think this is but it's been important, and it doesn't cost any compute typically. Best event sampling, technically, you could argue it costs more compute, but that can produce massive gains, more so than much more compute training time if you're in the pre-training stage. So yeah. What else? Oh, nice. I love this. Getting in the mix. Okay, so graphics tuning, in what sense? Oh, yeah. Okay, I can repeat. I think you're saying for this task, you can use embeddings. Is that the premise? So what would be the improvement? Yeah. Yep. Oh, so okay, so would the innovation be embeddings or what is the innovation? The optimization innovation. We can come back as well. Yeah, we can come back. Okay, nice. Someone had their hand up.
Hi.
Oh, wow.
I may have a few. Like,
Yes.
first of all, in context learning, maybe.
Yes.
Then
yeah.
we get something like reflection, then chain of thought,
Yes. Yeah.
tree
All
of
the bingo
thought,
card. Nice.
then of course RAG.
Yes. Bingo card. Yes.
Yeah, I'll just go through my buzzword list at the moment. Yeah. What's more? Yeah, increase context window size.
Bravo. Yeah.
Maybe mixture of experts.
Excellent. Yeah.
Yes. Yeah, let me think for a second. Agents, yeah, agents always good. Yeah.
Okay, so this is basically sweeping the bingo card. Nice. Excellent. Okay.
Okay, yeah, that's it.
Yeah, do you want to add one more for?
Oh.
That's fair. That was a clean.
Did we already say prompt tuning? I think yes,
I
right?
think we did. We kind
Okay.
of got at it because
Damn
we
it.
did. Yeah. So, but this is excellent. Bravo. Yeah, I
Yeah, we
know.
just
Clap.
discussed it.
Yeah. Nice. Thank you for starting the slow cap. That deserved it. Okay, perfect. Yes. So this
Things like flash attention.
flash attention, again, it kind of gets at the main goal there is to preserve performance while introducing a new objective of efficiency. But yes, efficiency is a very important objective. And so, yeah, that's fair. That's fair to add. And there's many other things we can talk about if efficiency is our objective that were very pivotal over the last. Yeah, go ahead. One more. Yeah, yeah. Yeah, this is actually very important. I would say that in general initializations, right? When we do massive pre-training, really we're doing conditioning of an initialization space. So you can think about that in the multilingual context, but things like RLHF, for example, don't work well unless you have pre-training first and then instruction fine-tuning, and then it's conditioned enough to be stable enough as a search space for RLHF. This is in some ways a really bad hack. Like, why do we have 3 stages of training? It makes no sense. Like, why do we have these non-cohesive structures of data? But it's mainly to condition a search space. And so, yes, I could see that as a motivator. Okay, so to start with, and we'll get to the full bingo list, let's talk about these 3. So multitask training, instruction fine-tuning, preference training. I'm going to go through these quickly because actually, I think the earlier lecture by Denki covered a lot of these very nicely. But I think of interest is also what types of properties lead to powerful zero-shot abilities. The abilities, and we can debate whether it's really zero-shot. We can debate if there's, I agree, I think sometimes zero-shot because of the whole issue with us not having a proper test set. It's hard to know if it's truly zero-shot, but there's undoubtedly sparser parts of the decision boundary where there hasn't been as many data points in the training data. These might be things like here, I ask, our coral model, I say, tell me a story about a wizard fish who goes to boarding school underwater. Maybe this is a less sparse, a less popular combination. And then it gives me this great story. But that's what we're interested in. And I would say 2 ingredients have been particularly important. One is instruction tuning. This came up, I believe, from the middle about the fine tuning. And this requires, it's not just fine tuning, it's the structure of the data. So structuring multitask fine tuning data as questions and answers. And this is a non-trivial change because this moves us from a single global model, which is what a lot of researchers focused on early in the last decade, to a global universal model. And now we're seeing a counter trend where now people want specialized models again, like a coding model. Or like Arabic specific model. But I think this is non-trivial to understand because it's a fundamental shift in how we do evaluation. It's caused a lot of the issues of the evaluation because we have to evaluate for everything. But it's also caused these nice zero-shot abilities to a large extent. And so we've moved from the single model to really not needing custom models for every task and using a single model for many different tasks. And then instruction fine-tuning, I think many of you are familiar with this, but it's just formatting it as this question and answer. So this combination of multitask training and instruction style improves zero-shot performance. And by the way, in terms of compute budget, this is very cheap because this is changes to the conditioning of the data space more than anything. So in terms of number of steps, you actually need far less data like this than you need for your extensive pre-training. And you actually need to update far less parameters. So going to the idea of routers, I think who brought up routers? There was a gentleman over there. Yes. So routers, going to that idea, often you can do this instruction fine-tuning only updating your routers, and it still ends up being much more performant. So in terms of compute and capacity, this is very cheap. And it goes against the idea that you just need more compute. It's really saying these changes to the task format are very equally important and have created massive jumps. And then preference training is really this idea that you're trying to align with human feedback. There's a lot of open questions here. We've actually done work that's really questioning, what are the components that we need for this preference training? And we have a recent paper, if you're interested in reinforcement learning applied to this problem, we have a recent paper called Back to Basics, which actually revisits the notion that you need very complex methods, and that this space in some ways is also very well conditioned because of all the steps that come before it, like pre-training and then instruction fine-tuning. And oh, I guess this is a cheeky slide saying our new IA model is great. Okay, so I think this snuck in. But this is this John Dang released this model, and we recently do this for multilingual as well. So preference training can actually lead to large jumps in ability. We actually show that IA 23 outperforms various other models. One of the biggest leaps was this applying both online methods like RLU, as well as even if you do offline methods like DPO, you can still get impressive gains. And so these are quite compute efficient, actually, if you think about it. What is other algorithmic improvements? I'm actually just going to go for it because I think our bingo card, a lot has been captured. Models which enable tool use. Tool use actually doesn't, it costs compute in terms of queries, but relative to compute for training time, it's quite cheap. Retrieval augmented models, basically no compute, especially if you do it at inference time and you have an associated database. It's really a combination of parametric and non-parametric, so extremely cheap. Chain of thought, ways that you prompt. Best of n sampling, you have more cost at inference time, so you're sampling the model more, so you have to pay for the forward pass. So there is a compute cost. But typically, the gains you get are much better return than spending the time on additional training. And actually, we often think of best of n sampling as just sampling a single teacher model. But some of our recent work has been shown about actually strategic sampling. So we call this active inheritance, and we sample from a pool of models to like steer the sampling. Distillation of synthetic data that came up, and increasing context length. So there's many, and these are very much very persuasive gains in performance. Now this idea that you have very large context length, you can add new information just by uploading a whole book to a context, and this adds new data. I want to talk briefly about the role of architecture. This is mainly, so if you were paying attention during this morning's lecture, now you get to show off a bit. So in 2012, everyone switched to deep neural networks. This is because they outperformed other available architectures in a persuasive way. So let's do this. Convolutional neural networks. What aspects of this architecture improve efficiency? What is it that improve efficiency here? Oh, convolutional neural networks. Yeah. Yep, go ahead. Excellent. Yes, very nice. And how is this? I think what you're talking about is like the efficient extraction of global information from using. So how was that done in convolutional neural networks? Shared weights, bravo. Yes, shared weights. So you had these moving filters, and they extracted patches of global statistics, and filters became specialized. So this led to the famous set of papers that was about like the kitty neuron or the kitty filter. That was thought to only extract or respond more strongly to kitty images. I think several papers followed that, which showed maybe there's not a kitty neuron, but the idea was that there's some notion of what these features are extracted, which differ, but the model can move across the whole image. This resulted in huge gains in efficiency. What else about convolutional neural networks? Translation invariance. Wow. Okay, bingo card. Nice. This is good. Yes. Equivariance. Yes. Yes. Yes, equivariance. Was that what you said? Oh, okay, very nice correction. So equivariance, yes. Yes, actually, this was the beginning of pre-trained networks. Yeah, and I think this is worth saying here because it's actually not being, this idea that you can adapt models easily to new tasks, it's really came into fruition with convolutional neural networks. So this is very important because you learn very general aspects of what natural images are. So yeah, very nice. What else? Rotational invariance? Okay, okay. So does that pass? Nice. Thumbs up. Yes, we have very nice points. Okay, anyone up there? Yes. Parallel computing. Bravo. What do you mean by that? Yes. So there was actually, so one of the reasons 2012 happened was that GPUs were made to play better with machine learning workloads. And in particular, matrix multiplies played very well with GPUs, and matrix multiplies dominate convolutional neural networks. So there's certainly something to be said for why this was a moment where it was efficient to train deeper networks, and deeper convolutional neural networks turned out to be the key factor and why they became empirically successful. So certainly that. We will talk about parallelism a bit more when we get to the next when we get to the transformer, but there is very much a sense that this was both a algorithmic and architecture definition shift, but it was only possible because of a hardware compatibility shift. Yes, go ahead. Pipelining. Okay, say more. Yeah, so certainly there's a very important fact about in general, data pipelines and compatibility with these algorithms. I wouldn't say that was an architecture prior to speak of, but I will say the notion of batches is very tied to deep neural networks, empirical risk minimization, where you just minimize mean error. So we'll talk about that a bit. But was there something else over here? Pooling, yes. Yes, bravo. Yes, this is bravo. This is bingo card. Excellent. Yeah, and actually, the most aggressive layers were max pooling layers, and this was almost absurd, right? We threw away all the information, but this made these architectures extremely efficient because you reduce everything. Yeah. Okay, I'm gonna move forward with this. So yes, so we had pooling operations, shared weight, hierarchical feature extraction. These are some of the benefits, and these are pretty hefty priors, right? Max pooling, famously, Geoffrey Hinton is furious at, and I get why, because there's no real reason max pooling should work, but it worked really well, and it just reduced dimensionality by throwing away everything but the max filter input, which is kind of crazy if you think about it. So these are very heavy priors on the search space. What about the transformer? So what made this? What aspects of this architecture improve efficiency? Yeah, go ahead. Yes, bravo, nice. We have the comeback of the parallelization. Yes, but here it very certainly was one of the key factors of scalability. It's very important. Yeah. Okay, what else? Do I see a hand down here? No? Okay. What else here? I mean, this one, I feel like these are easy points if you at this morning's lecture, you know. What else? Yeah. Yes, that's fair, but you do still have to backpropagate through the network. But yes, you avoid some of the saturation issues that happened for anyone who's had the pleasure of using an LSTM or an RNN. A little bit painful, yeah, but you avoid some of those instability issues, which, to be fair, is a non-trivial benefit because then you can typically go bigger if you have stable dynamics. So yes, that's fair. Yeah, go ahead, right at the back. Yes, yeah, that's not in there, but arguably you could say that the only reason pre-training worked was that you were able to craft an objective that could take advantage of pre-training. So yeah, that's a valid point. Yes, and then just in front, yeah. Layer norm, okay. Technically, a lot of architectures did have layer norm. Layer norm was first very much developed with convolutional neural networks in mind because of how deep these networks were getting. I mean, once you get to VGG, you'll gain really deep, and even there, residual networks introduce residual layers. But yeah, layer norm is a bit different. It's regularizing, and it did end up being quite pivotal in large language models because of the increases in size. So yeah, that's interesting. This is what I have. So I have self-attention, parallelizable nature, and then I do have something about the relative ability to absorb log context, which should make it much more efficient for processing long amounts of text. But I do think this is an argument in favor that the architecture design very much matters. And that architecture plus algorithmic innovation determine the rate of return for compute. And this is the truth. And this is also why often by just increasing compute, we don't have a precise notion of what that return is, because it doesn't alone tell the story of our field or progress. And what's often missed in this is that the architecture also determines the ceiling of returns. So our architectures typically are saturated over time. There's only so much you can exploit from a certain search strategy. So we saw this with convolutional neural networks. I believe we increasingly see this with transformers, which is why we get so much gain by restructuring the data in more powerful ways to exploit the architecture that we have. But almost certainly, this is not the finish line, so this architecture. This is really interesting because as a point of comparison, our brains are incredibly efficient. So we have 85 billion neurons, but we run on the energy equivalent of an electric shaver. And we have a few ways that are very important priors to condition efficiency. For example, you will largely simulate what I'm doing unless I do something dramatic, like move my hand here. If I stay like this, you're probably simulating what you're seeing. You don't do a full forward and backward pass. You also have specialized pathways. So it's easy for you to, for example, talk and walk. It's very hard for you to walk and eat, for example. There's different pathways that are much more optimized for speed. And you also have log scale vision. So it means that you don't pay attention to most things unless it's a notable change. And that's a way to protect you from absorbing and processing too much information. Excellent. Yeah. Yes. Yes. Yes, precisely. This idea that we can adapt our architecture is actually very efficient because what it means is we don't have to entirely retrain every time we learn something new, which is typically our most safe way to currently train architectures. We just retrain on everything, which is absurd. Yep, go ahead. Yes, yes, this is very nice. This is, I think, we have modularity. So although there are still active debates about what parts of our brain are attributed to what task, there's a general consensus like our frontal cortex is for forward planning. So if people have damaged their frontal cortex, it typically impacts longer term planning skills. We also clearly have the ability to have both short-term and long-term memory. This is non-trivial because how do you decide what is salient to convert to long-term memory? Whereas our networks treat everything with the same amount of saliency. They become frequency bound kind of counters. So there's no such thing as like a saliency. Whereas our memory, if you think about it, often what we remember is very rare events. It's not the most frequent events. So we have this ability to allocate proportional response based on importance and not just frequency of which we observe something. This is very, very important for efficiency. Yeah, very nice. Anything else here? Yes, please. Yeah. Yes, I heard there was an active debate about this. So analog, continuous, nice. So this is a very important point. Do we even have the level of precision to be able to codify? For example, there's the limits of our hardware and our software. I think about this a lot with sparsity. So this was brought up because our neurons are not just, our brain is not just modular, it's sparse. And so we have active pruning and regrowing of neurons over the course, most intensely when we're teenagers, but over the course of our lifetime. Sparsity, our whole computer vision and NLP and computer field has been built around the idea of static matrices, that you have something represented as a static matrix and that it is essentially represented from the get-go, and then you learn from that. But that severely impacts your ability to dynamically grow. Because how do you represent the absence of something in modern computing? Very difficult. Then you get to questions of the precision at which you represent something. And this also impacts. We know from quantization that there are trade-offs with the degree to which you represent. And even, this is very interesting, we did a very nice paper which showed that even the difference between bfloat, which is what is used in TPUs primarily, and float, which is used in GPUs, this caused very different, even at the same level of precision. So even if you do both at 16, bfloat 16, float 16, you had radically different sensitivity properties to quantization. Why? Because of the way that it treats outliers when you codify. So all these, even the type at which you encode, makes a subjective view of how the data is represented. Okay, and we've kind of highlighted this already. I want to do a quick time check. Where are we for time? What time is it? Ah, okay. So then we have to open for questions. Okay, so I'm just going to say I'm going to skip. Yeah, because it's more fun if we chat for 5 minutes and then everyone needs to go for dinner. So perfect. I'll just talk about very briefly some areas I think are important. Most of the issues that we have with the inefficiency of scaling, which is really the point I'm making in this talk, really that if compute is our answer, we're doomed because it costs so much to scale right now, mainly because we learn for the average of all our data. And so it takes a really long time or a really large amount of compute to learn the long tail. So the question I'll pose to you, the question I'm interested in right now is how do we learn the long tail more efficiently? We're very good at it as humans. How do we be better? Direction one we're working on is this idea of data, which has come up a lot today. If you skew the distribution, you can get away with less compute because you can skew it to the distribution you care about. I think that's interesting. Pay more attention to the data points you care about. The other is specialized adaptive compute. So how do you have modularity? I think mixture of experts right now is a very interesting direction, but it's more of an efficiency trick than it is true specialization. I think it's very interesting to think about how we can make it more actual specialization. But I'm going to pause there. Maybe we spend 5 minutes since we're a bit over on questions, and then we can continue afterwards over the next few days. I'm happy to keep chatting. Okay, questions. Is that okay, 5 minutes? Okay, and then we'll go for dinner. Nice. Any questions?
So before the question, before I forget, I may have an idea when you were making on how to perhaps learn the long tail more efficiently.
Okay, I love
We can
this.
chat about it later.
Yeah.
Now the question is, or rather the discussion I wanted to, the thing I want to hear your perspective on is, it's, I think as a community, so the notion of performance is a bit unclear. In particular, there's usually multiple axes that we want to improve on. We want to have good predictive performance, whatever that means. But then we also want to ensure things like a reliable model, a fair model, and things like this. What do you think is the philosophical way to approach these other things?
Yeah, and I've been kind of cheeky today because I've largely said, okay, acknowledge that efficiency, this is what would get you there. But for now, let's presume that we care about some notion of performance, which is not these alternative objectives, when invariably, if you're actually deploying models, you care about multiple objectives at the same time. So I do think for each of these subfields, typically the relationship, for example, in efficiency is very much how do you reduce compute for a given level of performance? For fairness, it's how do you constrain the objective, preserve general performance, yet constrain the objective for some secondary caveat to how you want your model to perform. And so these are all balancing a notion of trade-off with a general performance. Here, I've just talked about this general performance, but it is very true that inevitably you're going to be balancing more plates as you think about training your model. I still think this question of how we do that without throwing compute at it is valid. Efficiency anchors this explicitly as a goal, which is why I really like efficiency work. And I do a lot, our lab does a lot of work on efficiency because it's very nice. It's the definition of the subfield. It's like, why do we need so much compute? How do we do more with less? Other objectives are not so explicit. There's not as much understanding of how fairness trades off with compute. Oh, okay, go for it. I actually think that's a very, so typically it's framed as preserving performance, but actually again and again, we do find that, for example, reducing training data, but shifting to what you think can actually increase performance. So I do think a lot of what I talked about today is saves you compute, but improves overall performance. And so I think that tension is changing. Whereas before, if you worked on sparsity, it was largely how do I reduce the number of active weights while preserving performance, and it was rare that you would be able to improve, although sometimes we showed for outer distribution. So yeah, I think this is nice. Maybe I'll take one more because I think we have to go for dinner, and this has been really nice, and we can continue. Yeah, so who would like to? Excellent. Yeah, gentleman in the middle. Yep. Yeah. Yeah, I didn't have a chance to talk about it, but maybe I'll talk about one paper we recently released 2 weeks ago that I actually think is quite fascinating as a shift. We turn this active inheritance and we steer the data sampling space to optimize for non-differentiable objectives, which traditionally have not been at the forefront because they're hard to optimize for. But what's nice about this is that in some ways this is only possible because of a market shift in the cost of data. Like historically, it was very hard to steer towards new properties for your model because it would involve extensive, expensive data collection that you'd have to go back out and collect more data. And here we show you can actually just steer how you sample and from what models to explicitly optimize for a non-differentiable objective. So it's quite nice. And I think this idea of data optimization is very exciting for historical reasons, that now it is possible to optimize in the data space. So that's one example. And by the way, I do think what you're talking about with Rich Sutton, I don't think he would say, I think if he heard this talk, he would perhaps say he is bullish on compute and he is bullish on representations that don't codify heavy priors. But I do think there's possibly a room for interpretation that's more generous, that he more than anything is bullish on things that are scalable bets. And in his mind, what's scalable is things which require less codification of expert domain. I think when he wrote that piece, he mainly thought about it in terms of symbolic approaches. Perhaps what I'm saying here, though, is that really, even if you believe that there's some benefit of compute, which I don't say there's not, there isn't, you get the main levers are never compute alone, because you need to have some way of conditioning your search space, and you need to have optimization around that search space. And I think that's the big mistake we've made. And it's kind of like Moore's law. It's very hard to deviate. Hardware architects got stuck in this for decades. Very boring work, adding more transistors. And we're now stuck in it. And it's largely because it's very hard to deviate unless you have a good hypothesis. And this is what I think is that evidence increasingly shows that we actually do get more gains when we look at the wider set, and that we can get away with a lot less. And with that, I will say thank you so much.